Hello everybody. Today we are going to study variation of conductance with dilution. Myself Dr. Digna Varghese. Variation of specific conductance with dilution. The specific conductance of an electrolyte solution decreases with dilution. As the dilution increases, the specific conductance or conductivity decreases. You know the definition of specific conductance or conductivity of an electrolyte solution is the conductance of unit volume of the solution kept between two platinum electrodes with unit area of cross section and kept unit distance apart. Once again, I will tell you specific conductance or conductivity of an electrolyte solution is the conductance of unit volume of the solution kept between two platinum electrodes with unit area of cross section and kept unit centimeter or meter distance apart. Okay. We know in a concentrated solution, there are number of ions are more closer. Okay. Their intra-ionic interaction or intra-ionic or intra-ionic interaction between the ions are more, so they are more close towards. Okay. But on dilution, the volume of the solution is increased. You can see here from the pictures given here, one is concentrated solution and the other one is dilute solution. Okay. In this, the ions are separated by a more distance than the concentrated solution. Therefore, the number of ions per unit volume of the solution is decreased here, okay, so that the conductance per unit volume decreases. On dilution, the specific conductivity decreases. Upon diluting the solution, the concentration of ions per centimeter cube or meter cube decreases and therefore the specific conductivity decreases, but molar conductivity increases. As we increase the dilution, okay, as we increase the dilution, the volume containing 1 mole of electrolyte increases so that the specific conductance decreases with dilution. On increasing, we are measuring the electrolyte solution, the conductance of the electrolyte solution of unit volume of the solution kept between two platinum electrodes with the unit area of cross section and kept unit distance apart. That is the specific conductance or conductivity. Okay. So on dilution or upon the diluting the solution, the concentration of ions per unit volume decreases so that the movement of ions decreases per unit volume. So the conductivity also decreases. This is an important point, that is the specific conductance of an electrolyte solution decreases with dilution. You can see here a solution or a solvent, that is aqueous solution is taken here. If we adding sodium chloride, 1 mole of sodium chloride to this solution, we will get the ions are dissociated in such a way that is it is a more concentrated solution, so the ions are more closer due to intrionic attraction. Okay. If we diluted the solution, that means we add again the water to this solution, but it contains the same 1 mole of electrolyte. Okay. So on dilution, the specific conductivity of the electrolyte solution decreases. That means that the same 1 mole electrolyte is present here, but the distance between the ions per unit volume is increases due to decrease in the intrionic interaction or attraction. Okay. So the number of ions per unit volume decreases when compared to the concentrated solution, so that the conductivity decreases. So on dilution, the specific conductance of an electrolyte solution decreases. Okay. Variation of molar conductance with dilution. The molar conductance of an electrolyte solution increases with increase in dilution. The definition of molar conductance of an electrolyte solution is that for a given electrolyte solution of a given concentration, the conducting power of all the ions produced from 1 gram mole of the electrolyte solution, whereas specific conductance means the conductivity per unit volume. Okay, here the 1 gram mole of the electrolyte solution, or the conducting power of all the ions of 1 gram of or 1 mole of the electrolyte solution. Okay, so the molar conductance of an electrolyte solution increases with increase in dilution. As the dilution increases, the molar conductivity increases, because we are measuring the conducting power of all the ions produced from 1 gram mole of the electrolyte solution. In the case of specific conductance, we are measuring per unit volume. As the dilution increases, the number of ions decreases per unit volume due to decreasing interionic forces between the ions. Okay, you can see here the lambda m, that is the molar conductance, is the product of K into V, where K is the specific conductance and V is the volume of the solution containing 1 mole of the electrolyte. Okay, it has been found that as the dilution increases, the K on the solution is, we know the specific conductance decreases, but it is more compensated here by increase its volume, okay, on dilution. So that here we decreasing its molarity, so that lambda m increases with dilution. K on dilution of the solution is more, which is compensated by increase its volume or decrease its concentration. Okay. The increase in molar conductance with dilution is seen both weak and strong electrolytes on dilution. Variation of molar conductance with dilution for a strong electrolyte. The increase in molar conductance dilution is seen for both strong and weak electrolytes, but the manner in which it occurs is found to be different for the two types of electrolytes. Here we are discussing the molar conductance with dilution for a strong electrolyte. Okay, the difference in behavior is, you can see here the plot of molar conductance versus square root of concentration. Here you can see for the strong electrolyte, the rate of increase in molar conductance with increasing dilution is rather slow for a strong electrolyte and at a particularly high dilution. Further, for a strong electrolyte, the molar conductivity reaches a limiting value. You can see here the limiting value at very low concentrations. This limiting value of molar conductance at a high dilution. Okay, that is the molar conductance at infinite dilution or limiting molar conductivity, and represented as lambda m raised to 0 or lambda m raised to infinity. Okay, So the rate of increase in molar conductance with increasing dilution or decreasing concentration is rather slow for a strong electrolyte. For a strong electrolyte, the molar conductivity reaches a limiting value at very low concentration. Okay, at very low concentration. This limiting value of molar conductance at high dilution is called molar conductance at infinite dilution or limiting molar conductivity. It is denoted as lambda raised to 0 or lambda raised to infinity. Okay. So, for a strong electrolyte, the increase of lambda m with dilution can be represented by the equation lambda m is equal to lambda m0 minus a root c, where A is a constant at a constant temperature. It depends on the charge of cation and anion for the given electrolyte. All the electrolytes of a particular type have the same value for A. That means for a 1:1 electrolyte, that is sodium chloride, potassium chloride, sodium nitrate, all the charges is 1 or the valency is 1 here. So it is a 1:1 electrolyte. For this particular electrolyte, the value of A is a constant. 2:1 electrolyte, that is calcium chloride, magnesium chloride. Here the calcium oxidation state is +2 or its valency is 2. For chlorine 1. So it is a 2:1 electrolyte. So it has these types of electrolytes have the same value for A. Okay, and 2:2 electrolyte. Magnesium, the valency or oxidation state is 2. Sulfate, it is -2. So it is a 2:2 electrolytes. The value of A is constant for 2:2 electrolytes. So A is a constant at a constant temperature. A depends on the charge of the cation and the anion in the electrolyte. All the electrolyte of a particular type have a same value for A. Okay. So the plots of lambda m versus root c is found to be more or less linear. Here you can see it is extrapolated to 0 value or 0 concentration. So it is more or less linear in accordance with the equation lambda m is equal to lambda 0 minus a root c. So it is a linear plot. Intercept value is lambda m0 and slope is minus a. For a linear plot, v is equal to y is equal to mx plus c. Okay. So here slope is minus a and lambda m0 is the intercept value. Variation of molar conductance with dilution. Here you can see the plot of lambda m versus root c for both strong and weak electrolyte. Okay, we know the increase in lambda m with dilution for both strong and weak electrolytes, but the manner in which it occurs is found to be different for different types of electrolytes. Okay, the difference in behavior is reflected in this plot. That is, for strong electrolyte, you can see the increase in lambda m with increasing dilution is rather slow when compared to weak electrolyte. And here the experimental curves of lambda m versus root c for a strong electrolyte is found to be more or less be linear in accordance with the equation lambda m is equal to lambda m0 minus a root c that we have already seen. So, but such limiting value for weak electrolyte is not here. Okay, it increases it's with the dilution. Okay, but in the case of strong electrolyte at infinite dilution, it reaches a limiting value at a high dilutions. Such value is known as molar conductance at infinite dilution. So a weak electrolyte, it fails to give a limiting value for lambda m in the measurable range of concentrations. Okay. So lambda m, that is concentration increases, lambda m decreases, concentration decreases, lambda m increases. Here you can see the behavior of a strong electrolyte on addition of water and its molar conductivity for a strong electrolyte and a weak electrolyte. Let us see the molar conductivity of two electrolytes here, that is KCl and for acetic acid. KCl is a strong electrolyte and acetic acid is a weak electrolyte. This table is only for understanding. Okay, you do not have to learn these values. So here you can see the concentration values: zero point 0.1 mole per liter, 0.05 mole per liter, 0.005 mole per liter, 0.001 mole per liter, and reaches a infinite dilution. So the concentration decreases in this direction, but dilution increases. Okay. So as the dilution increases for potassium chloride, that is a strong electrolyte, the value of lambda m is found to be increases to the bottom. But in the case of acetic acid, the value is higher, very high, and it's a rapid change. Okay, but this range is very slow. So we can say that the rate of increase in lambda m with increasing dilution is rather slow for a strong electrolyte, whereas it is much rapid for a weak electrolyte. Thus, that is, you can clearly understand from this table. Okay, so infinite dilution means the solution so dilute that its concentration or molar conductivity does not change with further dilution. Okay, for a strong electrolyte, the infinite dilution, the molar conductivity value is 149.9, and for a weak electrolyte like acetic acid, the molar conductivity 390.7. Explanation: the molar conductivity increases with increasing dilution or decreasing concentration. An increase in the number of ions, this is due to explained in terms of two effects, that is an increase in the number of ions and a decrease in the interionic attractions. For a strong electrolyte, the molar conductivity is high at even at low dilutions. Here you can see the molar conductivity value. Even at low dilution, it is very high value when compared to weak electrolyte. We we already seen from the chart that for acetic acid its value is about 5, then for KCl solution its value is lambda m value is about 129. So there is a huge difference between the strong electrolyte and the weak electrolyte. Sorry for a strong electrolyte, the molar conductivity is high even at low dilutions, since the ionization of the electrolyte is complete. Here you can see sodium chloride Na plus Cl minus. The ionization is complete. But in the case of ammonium hydroxide, this is a weak base. Its ionization is in equilibrium. That is ammonium hydroxide plus OH minus. Ammonium hydroxide is in equilibrium with ammonium hydroxide plus OH minus. So its ionization is not very complete. It is only partially ionized form. But in the case of strong electrolyte, it is completely ionized form. So with increasing dilution, that means when it dissolves in water, water is here, sodium chloride is dissolved in water, it is dissociated into Na plus and Cl minus. Between these ions, the water molecules enters. With increasing dilutions, the number of water molecules enters between the molecules. And so the molecules, the ions are the decrease in interionic attractions between the sodium and chloride ions due to the increase in the dilution. So therefore, the velocity of the ions and the conducting ability of the ions increases. Okay, so the sodium ion or chloride ions can easily move due to the increase in the velocity by decreasing the interionic attraction. So increase the number of ions here and also decreasing the interionic attraction and thereby increasing the velocity of the ions so that the conductivity also increase. So at high dilutions, the interionic attractions become negligible and the molar conductivity reaches its maximum value. known as limiting molar conductivity or molar conductivity at infinite dilution. Okay. For a weak electrolyte, the molar conductivity is low at low dilution since the electrolyte is only slightly ionized. Okay. With increasing dilution, that is, increasing dilution means more water molecules are added to here. So with increasing dilution, the molar conductivity increases because the separation between the ions is increases by that will undergo greater ionization here of the electrolyte. So as the dilution increases, the interionic attraction decreases. So this causes an increase in the velocity and thereby increasing the conductivity of the ions, conducting capability of the ions, and thereby contributes an increase in the molar conductivity. So towards higher dilutions, the effects due to greater ionization and reduced interionic attractions become so pronounced that the molar conductivity increases rapidly. So at a low dilution, the ionization is complete, so the number of ions increases, a decrease in interionic attractions occurs. At very high dilution, interionic attraction becomes negligible, capability of ions becomes conducting becomes increases. So the conductivity, molar conductivity increases with increasing dilution for both strong and weak electrolytes by increasing the number of ions and decreasing in interionic attraction that you can see here from the plot also. Degree of dissociation of weak electrolytes. Degree of dissociation or ionization of an electrolyte in solution at a given concentration is defined as the fraction of the total number of moles of the electrolyte that has dissociated in solution into ions. Here you can see the ammonium hydroxide. It is a weak base. It is dissociated into ammonium hydroxide and OH minus. Here you can see the degree of dissociation is calculated by using this formula, that is alpha is the degree of dissociation. So alpha is equal to lambda mc divided by lambda m0, where lambda mc is the molar conductivity at specific concentration. Here lambda m is the molar conductivity at infinite dilution. We can assume that at infinite dilution, when the limiting value of the molar conductivity lambda m0 is reached. Even a weak electrolyte at this infinite dilution, it is completely dissociated. Okay, its degree of dissociation. So therefore, the degree of dissociation of for a weak electrolyte is 1. Variation of equivalent conductance with dilution. It is the variation of equivalent conductance with dilution is exactly similar to that of the molar conductance. Lambda equivalent is similar to lambda m. So, but nowadays it is more commonly discussed in terms of molar conductance. So, not in terms of equivalent conductance. Okay. Ion conductance. At infinite dilution, the ionization of the electrolyte will be complete and all the forces of interaction or intermolecular attraction between the ions decreases. The contribution towards the molar conductance that each ion makes at infinite dilution is known as its ion conductance. Once again, I will tell you, ion conductance is that the contribution towards molar conductance that each ion makes at infinite dilution. Okay. Here, a comparison of molar conductance of sodium and potassium salts of the same anions. You can see here from the table. Let us compare the values of potassium chloride and sodium chloride first. The lambda m values is, you can see 130 and 108.9 ohm inverse per centimeter square. Its difference is 21.1. Okay. Next pair of salts, that is, potassium nitrate and sodium nitrate. You can see here the anion is nitrate, that is same here. So it's potassium nitrate, the molar conductivity value is 126.3, and for sodium nitrate it's about 105.2, and its difference is 21.1. So the same difference of 21.1 ohm inverse centimeter square is found for the lambda m0 values of any pair of sodium and potassium. Here it is lambda m0, infinite dilution value. So the conclusion that the salts having this of either a cation or anion of the common also provide the same results like potassium chloride and sodium chloride, or potassium nitrate and sodium nitrate. So the same difference value for lambda m0 for a pair of salts. So the contribution towards the molar conductance that each ion makes at infinite dilution is known as. Thank you for your attention.